Hi, today we can talk about how can we analyze a mixture using absorption spectroscopy or absorption spectrophotometric analysis of a mixture. How it works, the one should understand the basics of absorption spectroscopy like Beer-Lambert's law and also how to calculate epsilon and concentration of a material using UV visible spectroscopy. I already made a video regarding this. For your reference, I will keep the link below. Briefly, Beer-Lambert's law will work only on a particular or fixed wavelength. Then, how can we analyze a mixture? Mixture definitely will contain more than one compound and each compound will have different lambda max. So today we are going to talk about this issue, that is the absorption spectrophotometric analysis of a mixture, or how to find the unknown concentration of a mixture using Beer-Lambert's law. Before that, welcome to Psychopul official YouTube channel. If you like our video, please like and subscribe our channel. Suppose we have a mixture of two components, compound A and compound B. That is, the mixture means compound A and B. First, we can have a look on compound A. And the compound A has an absorption spectrum shown here. And it has a lambda max around 560 nanometer. Then we can calculate the epsilon A 560 nanometer using Beer-Lambert's law. Then what is this epsilon A 560 means? That is molar absorptivity coefficient epsilon of compound A at 560 nanometer. Suppose the epsilon A 560 nanometer of compound A calculated using Beer-Lambert's law is 0.0500 liter millimole raised to minus 1 centimeter raised to minus 1. And this compound A has no absorption after 600 nanometer. So we can calculate epsilon A at 630 nanometer and definitely it will be 0. Then coming to the compound B, that is the second compound. Compound B has the absorption spectra as shown here. The lambda max of compound B is at 630 nanometer. However, it has also absorption at 560 nanometer. So by using the Beer-Lambert's law, epsilon B at 630 nanometer is calculated and is given as 0.1 liter millimole raised to minus 1 centimeter raised to minus 1. Here it has no absorption after 650 nanometer, but it has absorption at 560 nanometer. So epsilon B 560 nanometer will not be 0 here and it is calculated and is given as 0.06 liter millimole raised to minus 1 centimeter raised to minus 1. Then mix the compound A and B to get the mixture of AB. The combined absorption spectra of A and B will result the absorption spectra of the mixture. The absorption spectra of the mixture having a lambda max at 630 nanometer and also has an absorption at 560 nanometer. Compound A has an absorption at 560 nanometer and compound B has absorption at 630 nanometer and also at 560 nanometer. If we use absorption at 630 nanometer and use the Beer-Lambert's law to calculate the concentration of compound B, Beer-Lambert's law is given as A at 630 nanometer is equal to epsilon B at 630 nanometer into concentration into path length. Path length is 1 centimeter. And absorption or the absorbance at 630 nanometer is 1, which we already obtained from the absorption graph or the absorption spectra. That is, epsilon B is also 0.1 and concentration we don't know, that is unknown, and the L path length is 1 centimeter and absorbance is 1. So by calculating concentration of C, we will get concentration C is equal to 10 millimolar. We can determine the concentration of B at 630 nanometer alone. Why? Because absorption of A at 630 nanometer is 0. So we need to consider only epsilon B, not epsilon A. Okay, so we calculate the concentration of B at 630 nanometer using that wavelength 630 nanometer and we got the concentration 10 millimolar. Then at 560 nanometer to determine the compound B using epsilon B 560 nanometer is equal to 0.06 liter millimole raised to minus 1 centimeter raised to minus 1. Using the Beer-Lambert's law, we will get the concentration of B as 11.5 millimolar, which is wrong. We overestimated the real value of B because compound A also absorbs at 560 nanometer. In reality, we must add Beer-Lambert's law together for compound A and compound B at 560 nanometer, like the equation shown below. That is, absorbance at 560 nanometer is equal to epsilon A 560 nanometer into concentration of A into path length plus epsilon B 560 nanometer into concentration of B into path length. For example, in this equation we can substitute all the values we obtained from the absorption spectra. We could get the concentration of Ca value and the concentration of Ca is 1.8 millimolar. So in this way we can calculate the unknown concentration of a mixture, that is compound A or compound B. If you have a mixture having 3 or 4 compounds, you can use the same method. The only difference is the calculation will be little longer. You can use the same method and you can calculate. In this way, we can calculate the concentration of a mixture having compound A and B, and we got the result of compound A having a concentration of 1.8 millimolar and compound B having a concentration of 10 millimolar. Like our video, please like and subscribe our channel. Thank you for watching.